This is our team member. First is Ismail, second is Ain Nabila, third is Kairatul Afika, fourth is Syazwani Adila. Introduction to GPS framework development. First is purpose and functionality of GPS. GPS is a satellite-based navigation system that enables precise determination of geographic location anywhere on Earth. It has become indispensable in various real-world applications such as navigation, mapping, asset tracking, and emergency response. Second is component of GPS framework. There are 6 types of component. First is satellite signal processing. It uses accurate location calculation based on signal from GPS satellite. Second is error correction. It is algorithm to minimize inaccuracy caused by atmospheric interference. Third is coordinate system, which is mapping geographic position to specific coordinates. And fourth is GPS receiver, hardware devices that receive and process satellite signal. Fifth is mapping software. It is used for user interfaces for visualizing GPS data. Sixth is integration with GIS, which is combination GPS data with geographic information and system. Next, it is key consideration. There are 5 types of key consideration, which is modularity, scalability, security, efficiency, and user interfaces. For modularity, it is designing components that can work together seamlessly. For scalability, it used to supporting the diverse application and user loads. For security, it is used to protecting against unauthorized access or tampering. Efficiency is optimizing resource usage for real-time processing. User interfaces is intuitive interfaces for user to interact with GPS data. Lastly is multidisciplinary approach. It is GPS framework development involves software engineering, telecommunication, and geospatial science.
Understanding GPS fundamental. So first, comprise a constellation of satellites that emit signal including position, time, and health status. 2. GPS receivers find their location by triangulating signals from at least 4 satellites. Satellite emit 2 principal signals, L1 which is 1575.42 MHz for basic civilian locating and L2 1227.60 MHz for more accurate use. There are encrypted military signal, PY code, and unencrypted civilian communication, CA code. Next, GPS accuracy can be affected by clock errors, ionosphera, and troposphere influence, multiple error, receiver noise, and bad satellite geometry. A GPS receiver operates in phase, picking up signal, monitoring signal, measuring time delay, estimating position, and processing data to compute precise locations. Next, understanding GPS error source. There are 3 GPS error and bias source. First, atmospheric effect. There are 2 components, which is ionospheric delay, influence GPS transmission speed, causing inaccurate distance calculation. Dual frequency GPS receiver can reduce this inaccuracy. Next, tropospheric delay causes GPS signal delays due to water vapor in the troposphere. Second, satellite error, clock errors. GPS satellite precise atomic clocks are not fully synchronized, leading to signal timing inaccuracies. GPS receiver use data from many satellites to estimate and correct clock bias. Ephemeral errors. Satellite broadcast ephemeral data which may contain minor mistakes due to gravitational pulls. And lastly, multi-path effect. Signal reflection. GPS signal bounce off obstacle leading to miscalculation of real distance to the satellite. At once, GPS receiver mitigate multipath effect using signal identification and filtering. Effect on GPS accuracy in practical application. First, navigation and mapping. Inaccuracy result in location accuracy of a few meters. Second, aviation and maritime. Revision GPS, DGPS, and augmentation system increase accuracy by sending corrective signal. Third, surveying and geos. Technique like real-time kinematic RTK, positioning, and precise point positioning (PPP) deliver centimeter level precision. And lastly, agriculture and autonomous vehicle. Advanced GPS technology like RTK and optimization system are used for precision agriculture and autonomous vehicle navigation.
Identifying real-world application. So, the importance of GPS in precision agriculture. So, GPS technology improves crop management by identifying zones requiring specific management approaches. It optimizes resource use and promotes better crop growth and harvest. GPS technology improves efficiency and output in agriculture by reducing overlap and gaps during planting, fertilizing, and harvesting. So, it reduces environmental impact by enabling a variable rate application, reducing chemical consumption, and minimizing environmental damage. In GPS technology enables complete data collection and analysis, allowing real-time tracking of crop health and yield data. Challenges associated with GPS implementation. So, in large initial investment, the cost of GPS technology, suitable machinery, and software can be high, especially for small and medium-sized farms. In technical challenges, GPS signals can be interrupted by obstruction, resulting in inaccurate data collection and machinery performance. So, in data management, the massive volume of data created by GPS and related technologies needs effective data management and analysis tools. For training and adoption, farmers require proper training to use GPS technology and analyze the data it generates. So for connectivity concern, poor internet access can impair the performance of GPS with solutions that rely on real-time data transfer. So in GPS technology has the potential to transform precision agriculture, increasing efficiency, productivity, and sustainability. So however, to fully realize its promise, these challenges must be solved.
For requirement analysis, first is accuracy, 1 until 2 meters in urban and 3 until 5 meters in rural areas. Second is road accuracy, ensures road alignment with road network. Third is reliability, maintains reliable GPS signal reception in various environments. Next is system uptime, ensures high availability and minimal downtime, 99.9% uptime. Next is a power consumption, optimize power consumption for battery operated device. Then is a sleep mode, implements power saving modes when high accuracy is a need. Next is environmental conditions, operates effectively under various weather conditions. And last is a temperature range, functions within suitable vehicle use temperature range, -20 to 70 Celsius.
Implementation and validation. So the integration of Kalman filtering, neural networks, and machine learning algorithm into GPS technology significantly enhance accuracy, noise reduction, and predictive capabilities. The process began with defining objectives and requirements, identifying hardware, data resource, and computational resources. Data collection is crucial, including raw GPS data and additional data from sensors like accelerometer, gyroscopes, and magnetometers. Data reprocessing ensures data integrity and temporal alignment, while the Kalman filter is applied for initial state estimations. The Kalman filter is established before integrating neural networks and machine learning. Engineering is done by extracting essential features from raw and pre-processed data, merging GPS and sensor data, and identifying appropriate machine learning models. The trained models are combined with the Kalman filter to improve overall accuracy and prediction capabilities. The combined Kalman filter and machine learning model are loaded onto the target hardware for efficient computing resources and real-time performance. GPS framework validation overview. So, validation is a crucial process for ensuring a GPS framework meets accuracy and performance standards. It involves utilizing simulated and real-world data to evaluate the framework capabilities. Simulated data validation involves testing the framework in various environments, including urban canyon and rural areas. Real-world data validation involves field testing, benchmarking, cross-validation, and statistical analysis. So, robustness testing tests the framework sensitivity to noise and potential failure scenarios. User feedback and iterative improvements are also essential. Performance monitoring ensures long-term stability and constant performance under changing situations. Data collection and pre-processing. GPS framework modeling data collection. So in GPS uses satellite for pictures location data. A variety of data sets are needed. Signal data, ambient variable, geographic information, and reference station data. So the process involves acquiring various data sets, emphasizing their importance and collection strategies. So in GPS signal data collection overview, raw GPS signal are crucial for GPS modeling. Measurement includes pseudo-range, carrier pace, Doppler shift, and signal strength (SNR). Pseudo-range estimates distance to each satellite using time delay. Carrier pace measurement allow to precise distance computations. So Doppler shift data determines receiver velocity. Signal to noise ratio (SNR) evaluates the quality and dependability of received signal. So ephemeris data including satellite orbit and clock correction is collected via GPS satellite navigation signals. So position calculation are based on observation data from GPS receiver. Environmental data collection in GPS signal accuracy. Environmental variables significantly affect GPS signal accuracy. Ionosphere, a layer of charged particle, affect GPS signal speed. Total electron content (TEC) maps from global monitoring networks provide information on charged particle density. Weather condition can cause delays in GPS signal. Meteorological station or weather service collect weather data to model and correct tropospheric delays. This information aids in constructing accurate atmospheric models to reduce environmental impact on GPS signal.
Geospatial data collection for signal blockage and reflection. Digital elevation model (DEM) provide comprehensive topographical data for identifying signal pathway and prone location. These models sourced from GIS database are crucial for high accuracy GPS application. Data collection on building roads and other structure is necessary in metropolitan context with multi-path effects. Urban infrastructure data aid in determining the impact of reflected signal and devising mitigation techniques. Data can be gathered from the urban planning database for GI or GIS sources. Ground reference station data collection. Crucial for improving GPS accuracy through differential collection. Continuously operating reference station (CORS) provide high accuracy reference site. Access to CORS data is required for high precision GPS modeling. Differential GPS DGPS station adjusts for satellite clock problems, atmospheric delays, and other errors. The GPS data enhance GPS positioning accuracy essential for high precision applications like surveying and geodesy. Data collection technique for GPS modeling. Data logging with high quality GPS receiver is crucial for raw signal data. Accessing data from CORS and DGPS network is essential for high quality reference data. Remote sensing and ground surveying approach including UAV deployment are used for high resolution DEM and urban infrastructure data. Meteorological data survey provide real-time and historical weather data for tropospheric and delay modeling. Global Ionospheric Monitoring Network provide TEC map and other ionospheric data for precise adjustment. Modeling the GPS framework involves collecting GPS signal data, environmental variables, geospatial information, and reference station data. Various data collection approach can boost positioning accuracy, support diverse and application.
Next is case study. The title is Designing a Smart Bus Tracking and Monitoring System Empowered by IoT Technology. The objective of this project is to develop a smart bus tracking system using Blink and GPS Neo 6M. The problem statement is about, first, transport systems still use manual scheduling method that lead to lack up-to-date information about the status of buses. Second, limited availability of real-time and accurate bus location tracking system in terms of route and ETA. Third is upon the bus arrival is completely occupied by students, leaving no available seats. Next is solution overview. This project to address these challenges, which is hardware GPS that use GPS module, sensor ESP32 as microcontroller. Second, central server that use aggregate data APIs for communication. And third, mobile app, which is Blink, that can provide real-time bus location, estimate arrival time.
Modeling methods for GPS framework. First is satellite signal modeling. Key modeling methods include propagation delay, ionospheric delay model, tropospheric delay model, and multipath effects. Second is positioning algorithms. First is trilateration, calculates position based on the distance from multiple satellites. Second is Kalman filter, an optimal estimation algorithm that fuse GPS data with other sensor data to improve accuracy. Third is sensor fusion, combines high-frequency IMU data with low-frequency GPS data for a stable and accurate position estimate. And fourth, particle filter, a probabilistic model used for tracking and navigation in environments with significant signal obstruction. Third is error modeling and correction. First is receiver clock bias, models and corrects for clock bias and drift in the GPS receiver. Second is ephemeris and satellite clock errors, which use a broadcast ephemeris data and model to correct satellite position and clock errors. Fourth is geometric dilution of precision, which GDOP modeling, assess and minimize the geometric dilution of precision which impacts the accuracy of the GPS positioning due to the spatial configuration of the satellite. Next, for modeling methods for GPS framework is map matching, road network model, which use digital maps to match GPS positions to the most likely road segments. Then, hidden Markov models, HMM, models the sequence of GPS positions to determine the most likely path on a map. Next is path planning and optimization. Graph-based models represent the navigation environment as a graph and use algorithms like A or Dijkstra's for path planning. Next, for the modeling methods for GPS framework is simulation and testing models. First is Monte Carlo simulation, models the impact of various uncertainties and errors in GPS signal propagation and positioning. Then hardware in the loop, HIL simulation, integrates real hardware components with simulation models to test the GPS framework in realistic scenario. Last is environmental and contextual modeling. Urban canyon modeling simulates the impact of tall buildings and urban environments and on GPS signal reception. Then it context-aware models adjust positioning algorithm based on the environment.
In conclusion, the development of a robust GPS framework is pivotal for enhancing the precision and reliability of geographic location service across various applications. This assignment has highlighted the importance of integration sophisticated modeling methods to ensure the accuracy, efficiency, and scalability of GPS system. By addressing challenges such as signal interference and data integrity, the framework can support a wide range of functionality from navigation and mapping to asset tracking and emergency response. Furthermore, future research direction in GPS framework development may focus on improving real-time processing capabilities and integrating advanced technology like artificial intelligence and machine learning. This advancement could enhance signal processing algorithm, optimize position calculation, and predict location-based trend with higher accuracy. Additionally, exploring the potential of GPS with emerging technologies such as 5G network, augmented reality AR, and autonomous system could open new avenue for innovative application. This continued research and development effort will be essential to address evolving challenges and harness the full potential of GPS technology in increasingly interconnected world.